The following is an original production of AZPM News.
Arizona Science is supported by Research Corporation for Science Advancement.
For Arizona Public Media, I'm Tim Swindle, Professor Emeritus of Planetary Science at the University of Arizona, and this is Arizona Science. Joining me today is Jess Barnes, an Associate Professor in the university's Lunar and Planetary Laboratory. Welcome, Jess.
Thanks for having me.
You've been studying samples brought back from the asteroid Bennu by the Osiris-Rex spacecraft mission. First, why Bennu?
That's a great question, Tim. So Bennu is one of a few, maybe a handful of asteroids that we think are close enough to Earth that we could get there pretty quickly in space travel terms, but also might represent a body like those that might have delivered the ingredients for life to Earth. So Bennu is a carbon-rich and water-rich world that's close enough for us to get to explore with a spacecraft.
You've done all this great work, but how much of the sample did that really take, and how much are you going to be using?
I should mention the team is, 200 strong. We're present all over the world, studying these samples. And ahead of getting the samples back, the mission had a requirement to bring back a certain amount of sample. And that requirement was 60 grams. So if we didn't bring back 60 grams, we didn't meet that level 1 mission requirement. In the end, we brought back double that amount, which is great. And it's akin to maybe a small chocolate bar sized if you added all the sample material together. So it's a very small amount of material, and a terrestrial geologist would kind of laugh at that amount, right? But space missions are hard. We could only bring back a certain amount of material, and for us it was double the amount we were expecting.
What are some of the most dramatic things you've discovered about Bennu from the samples that you've had a chance to look at?
So first of all, the samples are absolutely spectacular. They represent a treasure trove from which we can understand not only how Bennu formed, but all the way back to the ingredients that might have been accumulating into the parent asteroid from which Bennu came from. In terms of what the samples are themselves, they're very fragile, carbon-rich, hydrated materials, full of clays, and they contain a range of minerals that we weren't necessarily expecting, even based on the spacecraft data we had for the asteroid itself.
Do these look like meteorites that have been found, or are they somehow different?
So in some ways they are similar. They don't have what we call a fusion crust on them, which we typically find on meteorites on Earth that's related to how they fall through the atmosphere. It makes sense we don't see those on Bennu because we went to the asteroid and collected them, right? And we protected them from Earth's atmosphere during re-entry in the sample return capsule. And then we've been very stringent about how we protect them in the laboratories on Earth. And so in some ways, they don't have those fusion crusts, but the mineralogy, to a large extent, but not totally, is similar to some types of meteorites that we have for study on Earth. So carbon-rich chondritic meteorites that we think represent the leftovers of planet formation. There are certain types of those meteorites that are very hydrated and also carbon-rich that spectrally provided a good match to the asteroid Bennu as we were surveying it. So we thought ahead of time, before looking at the samples in the laboratory, that these meteorites might be good analogs to Bennu. But there have been some surprises that we've learned that indicate they're not quite identical, if you like, to the materials we've brought back from Bennu.
What are some of those surprises?
The samples we brought back from Bennu are rocks, essentially, and they're made up of minerals. And some of the minerals that we found, although they're in low abundances in those return samples, they're unlike minerals we've previously seen in meteorites, even those that are thought to be analogous to asteroid Bennu. And some of those minerals are things like salts. We think we don't see them in the meteorite counterparts because terrestrial alteration may have meant that those minerals react very quickly to Earth's environment, Earth's atmosphere, water in the atmosphere. Or those meteorites have been sitting at the surface of Earth waiting to be collected by expeditions that go out to collect meteorites, and those minerals were lost, again, during interaction with Earth's environment. Or maybe lost during atmospheric entry. And so there's a record that we're missing from the meteorites that is preserved in these samples from Bennu because we've gone there, collected them, brought them back, and kept them safe.
You mentioned salts and clays. I mean, are some of these things that you really did not expect to find in Bennu?
Yeah, so we expected that they should have clay minerals. In fact, that was a prediction made early on before even getting to the asteroid and was tested at the asteroid with the remote sensing campaign while the spacecraft was orbiting the asteroid. And so when we brought the samples back, we wanted to further test that or double verify that that was correct. And indeed, the samples do contain a lot of clays. But what we weren't expecting, and again, based on studying meteorites for decades, and also remote sensing of the asteroid, we didn't predict some of the salts. So things like sodium-bearing salt, table salt, right? We find table salt in the return samples.
You talked about having salts and clays and things like that. How did these pre-solar grains survive the kind of things that created salts and clays?
That's a great question, and we're still trying to investigate that. The pre-solar grains are these bits of stardust that seeded our solar system, and they have different mineralogies. And different mineralogies, whether it be silicon carbide or graphite or some oxide minerals, the different minerals have different resistances to interaction with fluids. And so when we're going from the pre-solar grains that are kind of among the initial materials that would have accreted to form the parent body of asteroid Bennu, those different grains would have, to different extents, survived that alteration that subsequently happened to create the salts that we see.
You said this would have happened over a few million years. That sounds like a long time, but Bennu's older than that, correct? Or at least the parent? How old is it? Have you figured that out?
So we have not yet published the age data for the Bennu samples, but we have testable hypotheses that have been set up. And so we can put a framework to these things. 5 million years to us, humans, sounds like a long time, and it is, but in geologic terms, it's a blink of an eye. And so we think that our solar system formed about 4.567 billion years ago. And then within the first few million years of solar system history, we would have started to form some of the earliest rocky bodies in our solar system. We would have started to accrete Bennu's parent asteroid. Bennu is a fragment of a much larger parent body. And within that short time frame, the 5-ish million years, we expect, based on context from other sample types, we would have had initial accretion followed by parent body processing or geologic processing of the parent asteroid.
You say that it's a fragment of the original asteroid. Can you tell when it broke up and how?
That's something the team is working on from a sample perspective. We have a framework or a set of hypotheses for how that may have happened and when, based on things like understanding the dynamical evolution of the asteroid and trying to work backwards from where we see it today in space. So it's in near Earth space right now. It wasn't formed there, right? It was formed through these dynamical simulations and models, we think, and also based on what Bennu looks like spectroscopically. We think it might relate to some families of asteroids that are currently present in the asteroid belt. And so we can work from the dynamical point of view, linking Bennu as it appears today to those asteroid families in the main belt. And then from the sample perspective, work the other way. So understand what's the oldest material in the Bennu samples, where do we think in the solar system those materials formed, and try to reconstruct its history. And we can get a fair ways from studying these tiny little grains that were returned from an asteroid. We can start to piece together the solar system's history.
What's up next for your group in terms of Bennu? What are you going to study next?
So we actually just finished some measurements. We're really interested in understanding the aqueous alteration. So I mentioned that Bennu's parent asteroid accreted with ices. We get that understanding from the fact that Bennu itself is hydrated. It has these clays. It didn't form that way. We had to form those clays through the action of fluids on the original asteroid parent body. And so we really want to interrogate that fluid chemistry. We want to understand what was the nature of the ices that accreted to the parent asteroid. Where does that have to happen? And this is all to understand, the early days of Bennu's parent body, why it looks the way the samples look today, to better understand its geological history, But ultimately, one of the goals of OSIRIS-REx is not only to understand origins of the asteroid itself and what materials originally accreted to that to understand solar system evolution, but also to understand our origins.
Well, thanks for coming in and talking with us, Jess.
Thank you very much for having me.
Our guest today has been Jess Barnes, who has been studying the samples brought back from the asteroid Bennu by the OSIRIS-REx mission to understand the early history of the solar system. This is Tim Swindle, and you have been listening to Arizona Science. You can hear more of this conversation and others on our Arizona Science segments by going to the Arizona Science podcast at azpm.org.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science.
This has been an original production of AZPM News.